Hello everyone, and thanks a lot for joining me in this virtual presentation. My name is Julian, and on behalf of all authors, it is a pleasure to present our paper, Safe and Fast Tracking on a Robot Manipulator, Robust MPC and Neural Network Control. Let's have a look what kind of challenges we are still often facing in control for robotics. One possible example is control and path planning for automated or autonomous driving. And another one we often hear about is deploying robots in safety-critical tasks such as human-robot interaction. Even though these problems look quite different, they share some important properties and belong to a similar class of systems. Namely, they are both complex, safety-critical, uncertain, and constrained. I want to use this slide to show what we are doing to overcome these challenges. First of all, complexity in the form of high dimensionality and non-linearity is a big challenge, especially in robotics. Also, given the constrained nature of many applications, we think that a model predictive control approach makes sense. Additionally, many robotic use cases are highly safety critical, why we decided to propose a robust approach to also be safe under uncertainty. And last but not least, applications are often time critical or must be run on cheap, low power consuming hardware. To avoid the need to solve the optimization problem at each time step, we propose an approximate approach by using a neural network controller. However, different from many other neural network controllers, our approach retains the guarantees of the MPC in a stochastic sense. But let me now come to the mathematical problem formulation. We are considering disturbed nonlinear systems with state x, control input u, output y, and nominal dynamics f. Further, we assume a model mismatch in the form of a bounded disturbance. The state, input, and output is constrained by a compact nonlinear constraint set. Our objective is then, given an output reference yd, to exponentially stabilize the optimal reachable set point while ensuring robust constraint satisfaction. To better illustrate this problem formulation, I already introduced our experiment at this point. Set point tracking control of a robotic manipulator with obstacles. The goal is to track the reference, depicted in green, as close as possible in a safe way while not hitting any obstacles. So as shortly introduced before, we have the robust MPC and the approximate MPC, which is a neural network controller. As depicted here, both are connected via training and validation. We sample the robust MPC and use this for the training of the approximate MPC. And when the training is done, we again use the robust MPC to validate how good our approximation is. But let us first start with the robust MPC. A standard MPC is formulated as an optimization problem, with state dynamics f, an objective L, which is often a squared function to be minimized, and a compact nonlinear constraint set. In our case, this formulation does not work, since our goal is to track the desired output reference yd, and not xd and ud. To be able to use the standard formulation, we miss a mapping of this form, which maps the desired output to the desired state and input. For example, in our experiment, we define the three-dimensional end-effector position as output function. Therefore, mx would be the inverse kinematic, which is not always trivial to obtain and which we particularly avoid to compute here. Hence, we are not using the standard objective function, but instead this new one. As you can see, the first part looks similar to the one before, but does not require xd and ud anymore. Now, instead, we need xs and vs, which is an artificial steady state as introduced by Le Mans. Note that xs and vs are not known in advance and are part of the optimization. Further, we have a second part which makes sure that the output at our artificial steady state converges towards the desired one. So now, as we found the right MPC formulation, we want to propose a robust version of it to guarantee safety also under real conditions, namely uncertainties. For this new proposed robust scheme, we build up on previous cube-based robust MPC work. We handle a model mismatch within some known compact set W. Further, we assume incremental stability of the pre-stabilized system, which is a rather general assumption. V delta denotes the incremental Lyapunov function and is a metric which measures the distance between x and z. To extend the previous work to the case of set point tracking, we need to introduce new terminal ingredients. In particular, we introduce a new terminal set by adding two constraints to the optimization problem, which makes sure that the state at the end of our time horizon lies within the terminal set xf. xs and alpha are both decision variables. Here, the artificial steady state, xs, can be seen as the center of the terminal set, and alpha defines its size. In the paper, we show that this terminal set ensures robust recursive feasibility. So let me now just throw in the resulting optimization problem. First, we have the objective function for the setpoint tracking, as introduced before. Second, we have a constraint tightening based on a growing tube with zero initial size. And third, we have the new terminal set, which makes sure that the problem is robust recursively feasible under dynamic set points. In the paper, we show that we have guaranteed safety, that is robust constraint satisfaction, if the deviation between the nominal and the disturbed system in terms of the incremental Lyapunov function V delta is smaller or equal to omega d. Additionally, the optimal safely reachable set point is practically exponentially stable if the mapping from before is unique and the set of safe output references Ys is convex. This latter assumption is a very strong assumption, but it is important to notice that safety holds irrespective of this. Let us now move on to the approximate MPC. This approximate MPC formulation is also based on previous work, and its idea is very simple. Here, the ideal and implicit solution of the optimization problem gets approximated with a neural network. This, of course, leads to different state dynamics since we do not apply the perfect input anymore. However, what is special about our approach is that we account for the approximation error and uncertainty by introducing additional robustness. That means we design the robust MPC we learn from in an even more robust way to also account for errors introduced by a wrong p-approx. So when do we have safety for the approximate MPC? As seen before, due to our design, we can handle disturbances measured in V delta up to omega d. If we now assume for our model mismatch under ideal input to be smaller or equal to omega d model, then our approximate MPC is safe if the influence of the imperfect input on the nominal system is smaller or equal to omega d minus omega d model. But since our policy p-approx is given by a neural network, it is difficult to guarantee this over the full state space. Nevertheless, we can do this in a statistical sense. We show statistically that this inequality holds on IRD trajectories. For this purpose, we define an indicator function which has the value 1 if the criterion is met on all points along the trajectory and 0 otherwise. Then we sample p trajectories, which could be 20,000, 30,000 or whatever you prefer, the more the better, to calculate the empirical risk. This can be interpreted as the measured mean value of the random variable I. And then, by using Hoeffding's inequality, we can say that at least with confidence level 1 minus delta h, which could for example be 99%, the probability of the next trajectory to be safe is at least mu critical, which could for example also be 99%. Now our experimental results. First, you can see the robust MPC controller where the optimization problem is solved at each time step. We observe safe operation, and in practice it usually converges to a good solution even though the constraint set is not convex. In the second part, we now observe the approximate MPC. Due to its much faster sampling rate, the response time is a lot shorter, the robot is moving in a much more dynamic way. This can also be seen in this plot, which shows the tracking error over time, where the AMPC, depicted in blue, reacts a lot faster than the robust MPC, depicted in red. As a conclusion, I would like to summarize the contributions of our work. First of all, in the paper we proposed a novel robust MPC approach that extends recent work to setpoint tracking. Further, we also presented an approximate MPC scheme that improves upon previous work by providing a novel, less conservative validation criterion, and that also considers model mismatch. And last, this work shows the first experimental implementations of both the robust MPC based on recent work and the AMPC originating from citation 3. Furthermore, to the best of our knowledge, we showed the first experimental implementation of nonlinear tracking robust MPC with safety properties theoretically guaranteed by design. Thank you very much.